Math 1314, Tyler Junior College, Section 5.2, 3x3 Systems of Linear Equations. Solving a 3x3 system of linear equations. This is the natural progression from the previous series of videos, which was about solving a 2x2 system of linear equations. Recall that when you describe a system of equations, in other words, a collection of equations, one or more equations involving one or more variables, the first number in the description is the number of equations, and the second is the number of variables. Hence, 3 equations with 3 variables, x, y, and z. Also recall that linear means degree 1, meaning that the highest exponent on any variable will be 1. So let's solve it. Solve the system. X plus y plus z equals 16. X plus 2y minus z equals negative 1. 3x minus y plus 2z equals 35. So how are we going to do this? Well, if we reflect on the techniques for solving a 2x2 system, we might be able to find something we can use. Also recall that the plan of attack in solving a 2x2 system was to eliminate a variable so that we could solve for the other one. One plan of attack in a 2x2 system was to graph both lines and see where they intersect. 2 problems with that here. Number 1, because there are 3 variables, we cannot graph this in 2 dimensions. We would require a 3-dimensional graph, which is possible to draw in 2 dimensions as best as you can draw a 3D picture on a flat surface. But the other problem is the graphs of these would not be lines in 3 dimensions, that they would actually be planes, flat surfaces. So even if we could draw them, it would be hard to identify the exact point where not 1, not 2, but all 3 planes would intersect. If you want a visual, and I'm not going to move the camera, imagine the floor, the wall behind me, and the wall over here. They would all intersect in a single point, that corner of the room. That's the idea graphically. But because it requires 3-dimensional graphing and graphing a plane instead of a line, we're not going to take the graphical approach, although in theory it would work. Another approach was to use substitution, where we solved one equation for one variable and substituted it into the others. We could do that. For example, we could solve the first equation for x, and we would get an expression with y's and z's, and substitute it into the other 2 equations. But that would only take us from 3 variables to 2 variables, which isn't bad because we know how to handle 2 variables now. The other technique was addition, where we combine 2 equations and in an effort to eliminate a variable. We could do that also. For example, these first 2 equations, if we added them right now, the z's would cancel, but we would still be left with x and y. So of the 3 techniques, one of them we're not going to do graphing. And the other 2, I'm drawing a blank here. Substitution and addition will take 2 current equations with 3 variables and turn them into an equation that still has 2 variables. So how are we going to get out of this mess? Simple. If we can add 2 equations together and eliminate a variable once, for example, if we added the first 2 equations, the z's would cancel, and we would have a new 3rd equation that has x's and y's. That's not enough to solve unless we had a 2nd equation that also had x's and y's. So if we combined, say, twice the 2nd equation and the 3rd equation, I say twice because that would put a 2 in front of the negative z and cancel this, and that would give us another equation involving x's and y's. And once we have 2 equations with 2 variables, we know how to solve that. In general, our plan of attack for solving a 3x3 system is to first reduce it to a 2x2 system. So step 1, reduce to a 2x2 system. But let's be a little bit more specific than that. How are we going to accomplish reducing a 3x3 system to a 2x2 system? We can do it in 2 general moves. A, combine 2 equations to eliminate, well, let me rephrase this. use one pair of equations. Use one pair of equations to eliminate one variable. So you have some choices here. Pick a pair, any pair, and pick a variable you want to eliminate. Then B, pick a different pair of equations. Pick a different pair of equations, comma, but eliminate the same variable. So there's quite a bit of work right out the gate, but it's easy to describe what the plan of attack is. We need to pick two equations and get rid of the variable of our choice. Because there's going to be a lot of equations in this procedure, I'm going to number these equations 1, 2, and 3. So our first step is a doozy. Pick two equations and a letter to get rid of. Why don't we get rid of the z, and let's start by picking 1 and 2. If we take equation 1, which is x plus y plus z is equal to 16, and equation 2, x plus 2y minus z is equal to negative 1, this pair of equations is already set up to eliminate the z. So let's take advantage of that. If I add the equations, x plus x is 2x, y plus 2y is 3y, the z's cancel, 16 minus 1 is 15. I still can't solve for x and y, I have too many variables still. But now we're going to do the same thing with a different pair. It doesn't matter what pair you pick as long as it's not 1 and 2. So we can pick 1 and 3, or we can pick 2 and 3. I think I'm going to pick 2 and 3, but before I write them over there, let's think about how we're going to set up to eliminate the z. Because remember, different pair, but eliminate the same variable. To set up opposites on the z's, I can multiply the second equation by 2. So as I come over here, I'm going to write 2 times the second equation and the third equation. Let me put a dot in there to indicate 2 times the second equation. If I double the second equation, both sides, I'll get 2x plus 4y minus 2z equals negative 2. Don't forget to double the constant also. And if I bring the original third equation as is, I have 3x minus y plus 2z is equal to 35. And again, I've got the z set up to eliminate. Let's add these equations. 2x plus 3x is 5x. 4y minus y is plus 3y. The z's cancel. And on the right side of the equal sign, negative 2 and 35 is 33. I have two new equations. Here was the original 3. Our fourth new equation is the results of the first combination, 2x plus 3y equals 15. And our fifth new equation is the result of the second combination, 5x plus 3y equals 33. At this point, we have a 2x2 system. So our second step in general is to solve the new 2x2 system. In other words, do the same things we did in the previous videos. Let's bring equations 4 and 5 next to each other. Equation 4 is 2x plus 3y is equal to 15. Equation 5 is 5x plus 3y is equal to 33. Interesting. All right, so now we got to start over. How do we want to solve this 2x2 system? We could graph it, don't. We could do substitution, except all of these variables have coefficients besides 1 or negative 1, so that's going to unnecessarily create fractions. So let's use addition, meaning that we need to pick a pair to eliminate by multiplying by well-chosen numbers. I'm going to take advantage of the fact that the y's have the same coefficients. So they won't cancel now unless I multiply one of them by negative 1. Let's multiply the top equation by negative 1. I could have multiplied the bottom one. That will turn equation 4 into negative 2x minus 3y equals negative 15. And we're leaving equation 5 alone. 5x plus 3y equals 33. And now we can combine. Negative 2x plus 5x is 3x. The y's cancel, we set that up. Negative 15 plus 33 is 18. Divide both sides by 3 and we get x equals 6. So there's 1/3 of our solution because we need all three values, x, y, and z. Be careful, we haven't finished step 2 yet. Step 2 says to solve this 2 by 2 system. We've got half of its solution. Now we need the other half. Recall that to finish solving a 2 by 2 system, once you know the value of one variable, you can substitute it back into one of the equations in that system and solve for the other. Let's put it back into the original equation 4 before we hit it with the -1. 2x plus 3y equals 15. We think the x is 6, so we can substitute 6 for the x. 2 times 6 plus 3y is equal to 15. 2 times 6 is 12. So 12 plus 3y equals 15. Subtract 12 from both sides to get 3y equals 3. And then divide both sides by 3 to get y equals 1. At this point, we've done step 2. Again, the strategy here is to reduce the 3 by 3 system to a 2 by 2 system by creating 2 new equations that are missing the same variable. Pick one pair, eliminate a variable. Pick a different pair, but eliminate the same variable. Voila, 2 by 2 system. Solve it using the techniques discussed in the previous series of videos for section 5.1. But why are we not finished? We know what x equals, and we know what y equals. But the original 3 by 3 system also had a z. So your third and final step. Substitute the 2 known values into an original equation. So one of the equations we started with to find the third value. To find the third value. I know x, I know y, I want to know z. I need an equation that has x, y, and z. And I've got 3 of them. I think I'll pick equation 1. It's the simplest. We have x, we have y. Let's put them into equation 1. Equation 1 says x plus y plus z is equal to 16. X is 6, y is 1, we don't know z. 6 plus 1 is 7. Subtract 7 from both sides, we'll get z equals 9. You could write the solution as x equals 6, y equals 1, z equals 9. Or you could write what's called an ordered triple. An ordered triple is just like an ordered pair. But instead of having 2 numbers, it has 3 numbers. And instead of being x and y, it's x, y, and z. The x is 6. The y is 1. The z is 9. Hello, Ray Mysterio Jr. We'll do another example of solving a 3 by 3 system, but for our purposes, we won't explore these situations in this series where there could be no solution or there could be an infinite number of solutions. The no solution is easy. It's the same as before. When you run out of variables and get a false statement, it's over, no solution. The infinite number of solutions is a little trickier to describe. The scenario still occurs the same. You run out of variables and you get a true statement, but it's trickier to describe the solution set. We'll do another example in the next video.